First, I'd like to thank Eyal and Anat for the great job they are doing in Fuel Cell Initiative, especially for their support of the family of fuel cells, of the community of fuel cells and battery researchers in Israel, both in the academy and the industry. So their great support help us getting step function in our facility, in our research, in our development, and our achievement. So I would like to thank them a lot for their support. Okay, so the heart of a fuel cell is what is called MEA, membrane electrode assembly. It consists of proton conducting membrane, and on both sides there are nanoparticles of platinum or platinum alloy as catalyst. On one side we reduce oxygen, and on the other side we oxidize hydrogen. So all the researchers or experts in the field know very well that between 50 to 75% of the cost of a stack of fuel cell come from the Nephron membrane and the catalyst. So there's a lot of effort in the world, and also in my group, developing better and lower cost membranes and catalysts. So I will talk about catalysts of oxygen reduction, hydrogen oxidation, and two types of membranes, and also on some new storage, large energy storage system based on regenerative fuel cell. In order to save cost, we have to reduce the amount of platinum. So what we do, and other researchers does, we are working with a core shell, that we have a core of lower cost material and a tiny shell of 1 or 2 monolayer of platinum alloy. The issue is that when you're developing this kind of material, some researchers have published the results as is, they synthesize the catalyst, measure the activity, and publish. But this is not related to fuel cell technology. Because in the Nephron is very acidic, so if you build with this catalyst MEA, then you have leaching out of the catalyst material, the second metal, and the morphology and the composition of the catalyst change. So what you have to do is, if you want to get information, real information, relevant to fuel cell, you have to acid treat your catalyst first. So that's what we do, and all our catalysts are acid treated to simulate the situation in the fuel cell. So here you see some just example. We synthesized and studied over 100 catalysts, different nanoscale catalysts. Here you see some catalysts made of skin or shell of platinum on iridium, and we compare its activity to commercial catalysts. So in some terms, you see that we have the commercial catalysts have some 115 units of activity, and we have 278. That means our catalyst is 2.4 more active than gram of platinum. Here I show you that we really have a core shell. In this case, it's the middle section is ruthenium. You see the blue one, and you see two soldiers of platinum, and that gives you the proof that we are working with a core shell. Platinum is outside and a very low skin, and ruthenium inside. Here I show you the activity of hydrogen oxidation. It's also important. Another type of core shell, and in this case we are using only 15% platinum. In this case, another catalyst, 10% platinum, and we're able to increase the activity by a factor of 6 to 9. What that means, that if we increase the activity by a factor of 9, that means we can use 10% of the platinum per square centimeter of electrode area in order to get the same power or the same current density from the fuel cell. So this is a very good achievement. Another factor which is important is the Nephron membrane. It's a very expensive one, as I said, and it has several other problems. One of them is instability at high temperature, and if you see here a plot of conductivity versus temperature, its conductivity increases up to about 80 C and then fall quite quickly, and I extrapolate it widely to 120 C, and it comes close to 0. Therefore, most of fuel cells do not work above 80 or 70 Celsius. But it's good to work at higher temperature, then you can save catalyst, you can save on cooling system, and get higher power and better performance. We developed a novel membrane, proton exchange membrane, we call SASA. It's functional ceramic powder containing surface and core sulfonic acid, SASA, and PVDF binder. And what you say that we measure heat, you build from that fuel cells and measure cell resistance that goes down when we increase the temperature until 130 C, and we calculated the conductivity that goes up, although the numbers rising in this direction, so even in 130 C, we have still higher conductivity than at 80 C. But you see in the Nephron case, after 80 C, conductivity drops, and in the SASA membrane, conductivity continues to increase until 130 Celsius. We also run, with this cell, with this membrane, we run cell at 130 Celsius. So that's another project in my group that started about 15 years ago. And it's related to very large energy system, storage system. It composed of membrane, we call it NPPCM, that was produced in my lab, and catalysts that were developed in my lab. And the unique factor of this system is that we have the same unit, one unit that functions both an electrolyzer and as fuel cell. And this is unique in the literature. And it's very efficient one. Actually, we can use this electrolyzer to produce hydrogen. So when we want to save electricity, we electrolyze HBr solution to produce hydrogen tribromide that accumulate in the solution, and we feed the hydrogen into tank. When you want to get electricity back, just feed the fuel cell now. This power unit serves as fuel cell, and we got electric power and hydrogen bromide back. That this is a totally sealed system, no emission of solid and waste, infinite electrolyte life, and the efficiency is 75%. If you use a regenerative fuel cell based on hydrogen oxygen, the efficiency is 30%, 30, and here it's over 75. So you see here cycle life of single cell. This is one watt cell of a regenerative fuel cell. And you see this is charging, OCV, discharge, charge, OCV, discharge. We run this cell for over 10,000 cycles, very stable cycles. Now the energy efficiency, that means watt hour coming out from the system divided by watt hour coming into the system, is 79%. It is quite close to the values in batteries. I am a co-founder of a startup called InStorage. And InStorage just took our know-how and scale up the 1 watt system into 1 kilowatt, later on to 150 kilowatt. And today, together with Areva in France and Schneider Electric, they construct a 150 kilowatt grid-connected regenerative fuel cell based on our technology. It's now in construction. And the final blocking unit is 1 megawatt, 6-hour or 6 megawatt hour system. and thank you.